All right, well, welcome everybody to the event of Ramkumar Natarajan. So let's say Ram has been co-invited by Howie and myself for a number of years. And before then, I've known him. He was in the lab and also in the company. So it was a kind of a very exciting collaboration with Ram. He gave us an opportunity to explore the combination of search-based planning and continuous optimization. I think that's what he's going to talk about. He also gave an excuse to Howie and I to have a lot of more meetings than we usually have. So thank you, Ram, for that. I think we're going to see some really interesting stuff. And with that, I'll hand it over to Ram.
Thank you.
Sorry, so this is the student event, so that also means that, any sort of clarifying questions, by all means, ask them. But as far as the kind of more longer deliberation questions, leave those to the end so that we can have them during the questions. And then we have committee here, so Zach, obviously Howie and I, and then Ross Cedric is online, right? So
Yep.
Thank you very much committee for making it.
Cool. All right. Cool. So I'll start. Thank you, Max, for. Yeah, it is recording. Yeah. So thank you, Max, for that introduction, and thanks to my committee for being here and for providing all the feedback over the years. So today I'm going to talk about what I spent most of my time during my PhD on, exploring the connections between discrete search and continuous optimization for the application of kinodynamic motion planning. So I wanted to start by showing this footage, which is like this impressive demonstration of skills by these human pilots trying to drive this drone through these extremely huge clutter, right? So these.
Ram, sorry. Yeah, you're not sharing your screen on Zoom, so we're only seeing you.
Oops. Okay. Can you see now? Okay.
Perfect, thanks.
Is there someone else with the Zoom link?
Yeah.
With people in? Yeah, thank you.
Okay. Yeah, so I was showing this video to everyone on Zoom. So this is some impressive demonstration of skills by these human pilots trying to fly these drones through extreme clutter. But if you think about what is going on in their mind, they're trying to make so many decisions at runtime, right? So you're seeing, but then if you try to break down those decisions, there are these discrete set of decisions that they're making, whether to fly on every flight to the right or left of every single obstacle that they come across, but not just the next obstacle, several obstacles in front to decide what to do later. But at the same time, they're also actively controlling this drone and making those continuous fine refinements to dynamically enter these narrow gaps. So with that motivation, if you switch to something that is not in the air, like something that is in extremely confined space like this, where this person is trying to do some welding here, you can once again see that if you were to send a robot inside the space and help him, then you cannot have a robot that is extremely powerful, right? Like, because it's going to be right next to human and it has to be safety certified. With that, then you have to once again have these robots interact with the environment to do the heavy task, because they cannot lift a heavy object by itself. It has to get those forces from the environment and interact and make contact with the environment. So once again, we have these discrete set of variables, which is where to make contact and how to make contact, and the continuous set of variables, which is like optimizing and generating and moving through these contact locations. So what I'm trying to get at is we need to think of these two high-level discrete decisions and the low-level continuous decisions. But then, like, so we have these tools from motion planning. This is the planning problem, and we have these tools from motion planning, which can do these two things independently really well. So we have discrete or sampling-based planning that are very simple to use. They can easily be set up. I mean, many of these discrete planners are very unassuming with very less assumptions. They can guarantee these. They can systematically explore the space and give global guarantees. But mostly they're suitable for low-dimensional planning. Whereas you have these continuous optimization or trajop methods, which are fast, can be fast even in higher dimensional space, and they can incorporate these differential constraints. And they might be hard to set up, but then when you set them up correctly, they come up with these incredible, beautiful trajectories that you're seeing. But so, I mean, the people have tried to put these two things together. So there are like a number of work that try to combine these discrete methods and continuous optimization methods. But then I think what it boils down to is like how they are trying to combine them, right? So most of them take this hierarchical approach of doing these two things in sequence. So they first find these discrete decisions, set of these discrete actions to do, and then like through those discrete actions, they find the continuous solution. So, but then like that's a very myopic approach in the sense that there is no way for you to backtrack, or these two methods are not talking to each other. So there is only one directional communication, and there is no way for you to backtrack and do or change the discrete decisions if your continuous exploration is not going correctly, right? So, but then like it turns out that these methods actually work really well in practice. Like even if you're doing this hierarchical stuff, a lot of things that Boston Dynamics shows in their videos, they are pre-computed offline library of motions. And then like at runtime, they have this finite state machine or some kind of executive module that is trying to make these discrete decisions. And you have these library of motions following those discrete constraints. Many times it's also, these constraints are hand-coded by humans. And the same thing applies to the excavator that you're seeing or the Amazon robots that you see for doing the sorting task. But if you're not having that human expertise, or if you're not having that, if you don't have the bidirectional communication, then things can get tricky very fast. Like this is a very simple contrived example. Here you have this underwater snake in simulation trying to go deep into that confined space. What is happening here is that you have this discrete path of the head pose that is pre-computed, and then like you're trying to find a trajectory. So we are trying these different seed paths here, but it turns out that like none of them succeeds when you're doing this sequential operation. So I mean these things suggest that there should be a more of a unified framework that tries to, I mean, share this information between these two modules, and that's basically the theme of this work. So I think the fundamental motivation here is that we wanted to combine the benefits of these discrete search and continuous optimization methods. So, and in the central contribution of this work is this framework called INSAT, which stands for Interleaved Search and Trajectory Optimization. And I'll be talking very much in detail about this framework. So, so the research goal here is to enable this automatic discovery of these complex, global, long horizon and dynamically rich capabilities of these robots by seamlessly blending these discrete and continuous decisions into a single framework. But even for this, on this unified framework aside, we are not the first one to do this. Like clearly people have thought about this. In fact, the work on graphs of convex sets and its application from Russ's group, which was pretty much developed in tandem, has very similar goal. They have a different philosophy of going about how to solve that goal. But we'll see later in this talk how there are some benefits that my framework can take advantage of using their representation, and how their representation can benefit by using our solution. There is also these up and coming like bi-level framework for multimodal applications. So right now this is very new work. They are mostly focusing on local manipulation systems, and it's not that very general purpose. I think the most important note I have to make before going past the slide is the work on logic geometric programming from Mark Toussaint. I think this one, this is, in my understanding, one of the earliest works to start thinking in this direction of having a unified framework. It served as an inspiration for me, like when I started my PhD. But the thing is, like, some of the it's mostly developed for task and motion planning problems. And some of the formalisms that they make here do not easily extend to the problems that we see in motion planning. Okay, so that brings me to my agenda. So first, I will dive deep into this framework called INSAT, and then we will see some interesting applications of INSAT, which are pretty diverse in my opinion. So there is we are going to see like how can we apply it for rotor flight, and then also how to use it for planning with contact. Then we'll go into my last part of the talk, which is like you will see that INSAT starts to have trouble with its running efficiency. So we will focus on how to accelerate INSAT. And in that, I will be focusing on 3 different ways of accelerating. One is like CPU parallelization. The other is using rich planning representations to improve it. And then the last one is like, how can we use some pre-processing so that at runtime you can make the most out of it. So this forms the contributions of the thesis. So these works are all published in different venues that you see on this slide. Right. So first I'll go into INSAT. At a very basic level, INSAT. Yep. Is there a hide?
Hide video panel right there.
Video panel, so that's really fine.
Yeah. It made it worse. Okay, yeah, so I was saying that at a very high level, basic level, there is this graph search that is running and going to explore your lower dimensional abstraction of your whole planning space. Then we have the trajectory optimization that is running in your full dimensional planning space, right? So the key idea here is that we are going to use the search to call the shots and make decisions on what optimizations to run and with what initial guesses and seeds. And the optimization is in turn going to drive the search in the correct direction. So it is important that I emphasize that these two methods are being alternated and they're not running in sequence. So, and that's where the information flow is happening in both the directions, right? Okay, so this low dimensional space is typically the set of constraints that are kind of hard to model in optimization, right? So it can be obstacle space, which are usually hard to model with optimization. And then the full dimensional space, you have the rest of the variables. So before I explain INSAT, I wanted to start with like the most simple best first search algorithm, and then like I'll transition into INSAT. So I want to explain A star. So A star at every iteration, it maintains a frontier. If the frontier is basically something that separates the nodes that are already explored from the set of the space that is unexplored. So from this frontier, it picks a node for expansion at every iteration, and it generates a successor. So I'm going to use the word expansion to convert this node that is picked to a bunch of successors. And for these successors, it's going to update the cost of the successor using the incoming, using the node that is cost of the node that is being expanded. And once these nodes are, the costs are updated, we add these new nodes to the frontier and we keep going, and that keeps continuing. But then like if that node is already in the frontier, then you see if there is a better path to reach that node. And if there is a better path, then you update the cost of that node using that better path, right? So that's the update step if it's already in the frontier. The one thing that I want you guys to take away here is that A star only keeps track of the best path to every state, right? It doesn't keep track of all the other suboptimal possibilities for every state. So the reason why it can guarantee global optimality even by doing this is because it uses this assumption on optimal substructure of the underlying graph. And by using the optimal substructure, it is able to guarantee global optimality. And we will see later in our slides that for the problems that we are solving, this assumption wouldn't hold true, and we'll see how can we handle that. So now moving on to INSAT. So instead of these having just those nodes, now I'm going to couple all these nodes with a one-to-many mapping that takes you from these low-dimensional nodes to the full-dimensional space. So that is what is shown by these gray symbols here. So at any intermediate step in INSAT, you have these full-dimensional trajectories that is going from your start state to this one-to-many mapping. So we pick a node for expansion in the low-dimensional space. We generate the successors, and for that successor, we consider the ancestral path that is leading up to that successor. So you start from the most recent ancestor.
Yep. Are you projecting the slides? I'm not seeing the slides on the Zoom. Is it? Okay.
Okay. So for the newly generated successor, you're looking at the ancestral path and picking the most recent node, and you're doing a very short horizon incremental optimization that takes you from any point in between those two one-to-many mappings. And if that optimization converges, then you can use the incoming solution that you already have from your search to warm start this optimization and get this full dimensional trajectory all the way to the node that you just generated. But then if this trajectory violates some constraint, we have some mechanisms to handle this. But then, like if it still violates, then you go ahead with the ancestor before the most recent one and do the same thing again. So this way you get this full dimensional trajectory to the successor that you just generated. The takeaway here is that you're always using the recursion happening here to give very good initial guesses, right? So you would never add a node to your frontier if there is no existing solution. So, and using the dynamic programming, you are systematically exploring the space using the search in the low dimensional, and using that to drive the full dimensional space with very good guesses. And in turn, the solution of the full dimensional optimization is also making sure that the search doesn't explore random, like something that is uninformative. The second thing is, like, we are not doing this planning in the full dimensional space. We are deferring, and we are only selectively reasoning in the full dimensional space only when needed. And some difficult to model constraints can be handled in the low dimensional search because they can explore the space exhaustively. And then the last thing is, like, by doing this, you're doing simultaneous decision making in both these spaces. So I'll first then go into one application. So here I want to mention that the first two applications are something that I did before my proposal, and then the remainder of this work is done after my proposal. So I'm going to be spending less time on the applications and more time in the acceleration part. Okay, so for the application of quadrotor flight, the same picture that I was showing before, this is how it is going to look like. So you're going to have the flat, like the differentially flat output space, or just the configuration space of the quadrotor without the yaw angle in your graph search. And in the full dimensional space, you're trying to you're trying to find the minimum jerk trajectory here. So you have these derivative variables in the full dimensional space. But I mean, quadrotor is an interesting system because, like, you can find the direction in which the system has to accelerate at any point using the orientation. It can only accelerate in the direction perpendicular to its plane. So because of this dynamic inversion, you can impose some constraints in the full dimensional space as you search your low dimensional graph. So we use this attitude to impose constraints on acceleration, and you find these full dimensional trajectories, and that's what is now going to be used as cost to come, or is going to be used in the graph search. So with this, it's a very simple application. We were able to generate these really, like, and I think, in my opinion, cool trajectories, because, like, the task here is for these for the drone to fly from one side of the wall to all the way to the other extreme, and you have these set of parallel walls with these narrow windows that are smaller than the size of the quadrotor, which means that, and then the gap between these walls are also small, which means that it has to make sure it has to as the search, for example, goes close to the window to go through that gap, it might find that it is not having enough acceleration to generate that orientation. So the algorithm is going to backtrack and explore the space such that it can generate these helical paths between these walls to pump energy into the system and basically come up with that orientation to enter the subsequent window. We compared it with a baseline that was state of the art at the time. And we see that we are able to plan faster with higher success rate. And you get these global motions. We also tried it on some other environment here. This is a Willow Garage environment. You can see that there are parts of the trajectory which looks suboptimal, clearly. But that is because, like, in order to enter the gap that is coming later in time, it needs to take the suboptimal path to once again pump energy into the system and then enter that narrow passage. We have competitive times here, but in the cases where I think the time is higher, we have a higher success rate compared to the baseline. So then I'll talk about another application, which is the planning with contact. So before I go into that, I just wanted to give a very quick motivation. So like manipulating heavy objects in confined spaces is a challenging task, right? So you have these people trying to do so many things in confined spaces, like welding, like I showed before, or other stuff. And they go through a lot of physiological burden when they're manipulating heavy objects. So we wanted to, that was the motivation. And we have two different environments where we deployed our planner. So here, the robot is trying to manipulate an object that is outside its payload limit, heavier than the payload limit. And you can see that it is using the contact surfaces in the environment to come up with, to reason about the forces that it's getting from the environment and manipulate the object and generate those fine motions to transport the payload from one side of the environment to the other. We'll get into details later. So the high-level problem statement is that you're trying to find this trajectory that keeps the torque as low as possible, while at the same time respecting the torque limit. So it's very straightforward formulation. The only difference is that now you're allowed to make contact with the environment. So how does this diagram look like for this application? So the low-dimensional space is going to explore the quasi-statically feasible configurations of the arm. And then the full-dimensional space is where you're trying to reason about the joint velocity or the contact model parameters, which I'll get into in a minute. And this is going to keep alternating between the two to find the trajectories that I showed. So first I'll talk about the graph search setup. So you have this search running in the configuration space of the arm. And when you generate a configuration that is suppose in collision, we solve a very simple optimization using the contact normal. We are using Mujoko here. So I'm using the Mujoko physics to use those contact normals to find a configuration that is on the surface of the environment. And this is how the graph search is exploring the low-dimensional space. For the optimization, we are supplementing the Mujoko physics with some virtual contact force models that I developed. So this is because we wanted to, the contact dynamics are discontinuous. So I want to use, Mujoko is using soft contact model, but in order to make it more friendly to the optimization, I had this control over these virtual forces that that basically helps me start the optimization in a better landscape, and then like use and jointly optimize these contact model parameters to find the full dimensional trajectory. So basically, this is an instance of contact implicit optimization over the boundary conditions and the virtual contact parameters. For solving this, we use a risk-sensitive reformulation and use successive convexification, which is a hybrid approach that tries to use like LQR style rollouts and trust regions. So when we did that, we were able to test it in this environment first. So I'll first talk about the simulation setup and then go into the hardware experiments. So for the simulation, we have this. We wanted this robot to transport this payload, and we wanted to also flip the object. So this is a heavy object. We'll be evaluating it for different mass of the object. And the robot alone itself cannot lift the object at any configuration. So it has to entirely rely on contacts to generate these motions, right? So first, I'll just show you how the planner adapts and behaves for different payload masses, right? So here you're seeing from 1 kilogram to 4 kilogram, you can see that there is a increase in, like, I mean, the behavior, from the behavior, you can tell that it struggles more as you go towards 4 kilogram. But then, like, the most interesting thing for me is when we push the limits all the way to the 6 kilogram payload, the robot itself has a proximal payload limit of only 2 kilogram and distal payload limit of proximal limit of 4 kilogram and distal of 2 kilogram. So it's able to still move this object by entirely searching and exploring that very constrained manifold in your configuration space. And you can see these are the cylinders that you see here are the contact locations, and it's able to successfully move the object to the other side. So we also deployed this on the real system, and here you can see that we tested it for 2 different setups where you have the actual torque limits and the reduced torque limits. So the reduced torque limit is set in the software. And once again, you see that a difference in the behavior, that it takes more time and still ends up finding a solution for even with reduced torque limits. So there's one more task that I wanted to show here. This is once again a payload transportation task. You are transporting this 2.5 kilogram payload. But there is a slightly different constraint here because of the shelf wall that is behind the robot. You cannot go past a distance, and then the robot is unable to lift the object in its initial configuration. So what it ends up doing is it uses its wrist entirely to nudge and like get those initial, like finds those initial configurations to get out of the confined space. And then once it comes to the center part of the shelf, then it's in the distal configurations, and it's able to lift the object and turns around and places it on the other side and slides it in. So in terms of the torque reduction in hardware, you see that for the shelf transfer task, you see a saving of around 22%, and for the flipping task, you see around like 68% reduction in torque. So we also tested it for different heights of the partition, and we see that it's only our method that is able to complete the task without ever exceeding the torque limit in any of the joint. So there are some methods that produces lower average torque, but then they end up consuming more torque. They have a higher maximum torque, which means it's infeasible. So there is one more thing that I wanted to quickly show. So this is like when it ends up generating this purely dynamic motion of swinging. So you have this when you increase the payload to 4.5 kg, it cannot lift the object. So it just pulls out the object and swings to pump energy into the system and transport the object to the other side. So it's almost acting like a pendulum to get the object in. Okay, so I'll go back to the running example that I was having. So I was saying that in A*, you only keep track of the best path to every node. So I wanted to get back to that. So let's assume that if your low dimensional graph, this is basically, I wanted to talk about the optimal extension of INSAT called INSAT star. And I wanted to describe the conditions under which we can prove optimality. So the first assumption is that the low dimensional graph is basically a good abstraction, meaning that it can encode all the equivalence class of the solutions in the planning space. Assumption 2 is that we don't have any negative edges in our search space. This is a very standard assumption in search. And the last one is that we have a locally complete and optimal optimizer. What this means is that I was showing you that ancestral path in which we are trying to do incremental optimization and close the discontinuity. the assumption is that it's stating that in that equivalence class that you get when you take that low dimensional path to the full dimensional space, the optimizer is locally optimal. So under these assumptions, we have the statement of optimality that INSAT star is guaranteed to find a feasible trajectory in the full dimensional space if one exists that is optimal in terms of the solution cost. Cool. So that brings me to the last part of my talk, which is accelerating INSAT. And I'll first go into how can you use CPU parallelization to do that. So the algorithm that we developed is called PinSat. And so the inspiration here comes from a recent method that was developed in heuristic search community called ePace. So we used A star to explore the low dimensional space in INSAT. This can be easily modified to use a parallelized algorithm and without sacrificing any of the properties. So let's see how we do that. So what ePace does is basically it changes the basic unit of search from searching over states to searching over edges. And by this transformation, the search gets the flexibility to parallelize slow edge evaluations. And in INSAT, the slow edge evaluation basically means that making a call to the optimizer, which is basically slow. And if you look at this frontier, I have these different nodes in the frontier, and these are the different successors that come out of that nodes in the frontier. Normally, what you do is you maintain a queue of these nodes in the frontier, right? And the order in which the nodes are stored in the queue is the order in which the successors going out of the queue is evaluated. But instead of, and that basically means that you're making a call to the optimizer in INSAT. But instead of maintaining the queue over the nodes, if you maintain that queue over the edges, then you have the flexibility to reorder these edges. What that means is that you might just evaluate one edge going out of a state. And if that is promising, you don't have to evaluate potentially you don't have to evaluate the other edges going out of that state. And in some cases, when if such a successor is not promising, you also don't have to evaluate the other successors going out of the state. So this gives you the flexibility to parallelize multiple parts of the frontier at the same time. And if a particular direction is promising, then your search has the ability to brute force its way all the way to the goal without even evaluating any of the adjacent successors. Right, so this we tested this algorithm for these two different experiments where you have these basically the robot has to block a ball being thrown at it, and it has to reach that post exactly in time. In the top video, you have these multiple balls being thrown at the robot, and so the robot has to exactly intersect all these objects in time, and at the same time position itself in such a way that it can reach the subsequent ball more efficiently, right? Like it has to orient itself in that way. In terms of the results, we see that by using around 50 threads, you get 2 times increase in success rate and 4 times reduction in planning time. And we were also able to run this on the real system. So this is a demo that we had at the National Robotics Week. So here, I'll first explain the system here, and then maybe I'll go into how PinSat is used. So the system here is that you have this the system where, there is this person throwing a ball on the robot, and you have live perception that is looking for to detect these balls. But the challenge here is between the time the robot, in this system at least, between the time the robot sees the ball and the time the robot intercepts it, we only have 350 milliseconds. And in that 350 milliseconds, you need to predict, perceive the ball, then predict its future motion, plan what has to be done, and then execute the plan, like moving point A to point B on the robot. So this is a very challenging task in terms of the time it has, right? So we used PinSat to pre-process a motion library to generate these motions, and then that's what is executed on the robot. In addition, I think the people who funded our project were also interested in they want to put the system on a moving platform, which means that they want to reduce the amount of impact that the system creates on this moving platform when it moves. So we also had a lot of mean, we also had significant torque reduction in that moving platform. We have some results on that, but by using a kinodynamic planner, we were able to optimize for the reduction of torque in that moving platform. Cool. So one last time, going back to this example. So we have this, I mean, at this point, I think it should be familiar, like how INSAT is running. But let's say that this one-to-many mapping is actually, they're all convex sets instead of these one-to-many mapping, which can be arbitrary. And in addition to these convex sets, if you also have the relationship between the subsequent convex sets as convex constraints or convex cost functions, then you have a setup where in that ancestral path, the assumption 3 holds true, which is basically that you can find a locally optimal trajectory that I mean, globally optimal within that space, but locally optimal trajectory in the overall graph, right? So, and this is basically the graphs of convex sets representation. And in the next part of my talk, I'm going to see how I'm going to explain how the search methodology that INSAT has can help searching in this new representation faster, and how INSAT can benefit from by using this new representation. So that is the sophisticated planning representation. So just a quick background on GCS. So graphs of convex sets, I'm only going to talk about the motion planning application of it. It's a more general purpose framework than that. But in motion planning, it is it can enable this smooth kinodynamic planning by pre-processing the planning space and removes the expensive collision checking, right? And removing the expensive collision checking. So, and because it has these convex domain constraints and convex cost functions, this is very optimization friendly, and it can be empirically very sparse representation of the planning space. So a simple example, in your 2D environment, if you have these obstacles shown with these black polygons, you can decompose the free space into a set of these convex sets, and you can represent the adjacency relationship of these convex sets using the graph that I've shown below. This is like very similar to a multi-resolutional space decomposition, right? So planning on this graphs of convex sets is basically a mixed integer optimization where you have to simultaneously optimize for the sequence of convex sets on which your solution lies and the trajectory through that sequence. So, I mean, GCS opt was the method that was developed to solve this mixed integer optimization. So they come up with a very tight relaxation and do some rounding after the fact to find the monads of optimal trajectory. So so what is going on here is that the mixed integer part of the optimization is deciding what paths to choose and how to optimize the trajectory in that path. And the convex optimization is finding the trajectory once that path is chosen, right? So, and this is solved jointly. But then I think GCS underutilizes the power of the representation. So GCS is a very powerful representation. It's just that because of the choice of the solution strategy, it doesn't take full advantage of its representational power. It solves the GCS opt solves the same sized problem over the entire graph for every query. Basically, this means that the time or like the effort that the solution is putting is not proportional to the difficulty of the query. And it cannot take advantage of the graph search techniques because, I mean, although GCS is fundamentally a graph, because it's solving using an optimization method, it cannot take advantage of many of these search techniques that we have. It also does not enforce suboptimality before the fact. It can only calculate after the fact. This can be very useful when you're trying to speed search for just finding satisfying solutions, right? And we also see an example where completeness might be sacrificed. So for this example, like in the maze, the GCS opt method solves a same sized optimization that has 1.25 million constraints for every query, even if start and goal are right next to each other. So what we are saying is that we can use an implicit search method to search this new representation. In other words, we can use INSAT as a solver for this new representation, right? So that, and in terms of this diagram, how it's going to look is the low dimensional search low dimensional graph search is going to explore this sparse GCS graph, and the full dimensional optimization is going to optimize through that path that the search explores, like the path of the sequence of convex sets that the search explores. So this is how it's going to look like then. So you're going to start with a start convex set, and when you explore the space, you're going to explore the space of convex sets, and what I've shown with these highlighted convex sets are the path that you find in this low dimensional graph, right? And then through those sequence of convex sets, you can find these trajectories using optimization, which can be, because it's a convex optimization, you can find the optimal one. So, and then this proceeds until you reach the goal. But then there is a problem here, right? So you have changed your representation from having every state in your graph being a single state, or like every node in your graph being a single state, to every node in your graph being a set. And that basically means that you don't have this optimal substructure that you had in A star like searches anymore. So you might have to keep track of a suboptimal path coming into a state to eventually find an optimal path. That basically means fundamentally the Markov's property of the search does not hold. Meaning that like the subsequent successor, the cost not only depends on the state that is being expanded, but also the history of the states that is leading up to the successor. So how can we handle that? So the way we handle it basically leads to the extension, which is IXG star. That is the provably optimal variant of IXG. So basically guaranteeing optimality and completeness requires that you have the subsequence of path to a convex set also be suboptimal, and paths to revisit the same convex set multiple times, right? So these two requirements basically translates into allowing for state re-expansions. So when we apply that logic, and this is how the search is going to proceed, you're going to have states in your frontier, which are basically different paths leading up to the same state. And you need to, you now have to keep track of all those different possibilities. So, but then like, if you're going to allow for duplicates and re-expansions, then this is going to explode the search. Normally you don't want to do this, and not allowing expansions is not allowing re-expansions, one of the power of best first search. So how can we optimize it? In this paper, in this method, we propose two efficient lower and upper bounds to prune these re-expansions. And the lower bound is basically, we compute this lightweight data structure called a relaxed graph of convex set, which is a graph that you compute offline once you have done the decomposition that can take you between these states. So once you have computed this lightweight data structure, you can use this surrogate graph to compute heuristics and even warm start the optimization at runtime. So this relaxed graph is going to speed up the search, right? So how can we use it in the search? So you can use it in the search to check if a node that is being expanded, if the lower bound using this graph that I just mentioned, if it's greater than the upper bound, then you can just prune that node. So I also wanted to mention one thing about the completeness when a GCS vertex has to be revisited, right? So in this example, you have this a tractor trailer setup that is starting from this bottom configuration. It has to go to the goal, and it is facing this blue convex set. In order to find this system cannot go reverse; it can only go forward. And in order to find a solution for this, it has to enter the blue region and then come out of the blue region to go to the red region. So without some special handling, like GCSoft will in the vanilla version, it does not find the solution because you need to pre-specify a particular convex set has to be revisited, and you have to know the number of times it has to be revisited beforehand. Whereas by using IXG star, because you're searching the space implicitly and building the graph on the fly, you can figure out whether a region has to be revisited, and it ends up finding such a solution. So taking a step back in terms of the theoretical properties, so we have IXG and IXG star, which is the optimal variant, and we also have a weighted IXG and weighted parallelized IXG, which is basically suboptimal variance to find satisfying solution. And you have this property that IXG is complete under the assumption that any path on the GCS graph, the constraints along them can be satisfied, whereas IXG star and PIXG star are both complete and optimal. So we tested in the same setup where GCS opt was previously tested, and we see that we're able to find solutions for different suboptimality factors, and it is 4 times faster and 12 times more efficient in terms of the number of edges that has to be optimized. So I think the difference becomes bigger when you go to a larger environment. That's when things start to really be favorable, in the sense that when you have a very large graph, if you remember, GCS opt is still trying to solve the same size problem all the time. So instead, when you use IXG star, you're only incrementally optimizing a part of the graph of the whole planning space. And that gives us around 60 times faster planning times and 58 times more efficient in terms of the edges evaluated. We were also able to deploy it on a multi-arm motion planning setup. So here you have 3 arms trying to move without any collision between different configurations. So this is an 18 degrees of freedom setup. And we see that IXG star was able to solve and find solutions for this problem. Whereas,
Just want to point out that's a simulated arm, not a real.
yeah,
Yeah.
who has purple arms, right? So,
It just looks so good.
yeah, so but GCS opt was unable to load this problem into memory. So last thing, in terms of the savings that you obtain because of the incremental nature of IXG star, you see that even the largest optimization that was invoked by IXG star is only a fraction of what the GCS opt solves at every query. So if you were with me until this point, we are in the last part of the talk, which is how can we use some pre-processing to further accelerate the accelerate insight, right? So for this, I want to introduce another concept. This is a recently developed idea called constant time motion planning, which is basically a class of algorithms whose planning time is bounded, irrespective of what planning representation or approximation you use. The motivation here is we wanted to pre-process a motion library and use it for setups where the tasks are highly repetitive and the environment is mostly static, right? Like you see in this video. But the question here is then, how can we adapt inside to produce this constant time behavior? So before, I wanted to just briefly mention some existing constant time planners. So there are a couple of planners here which can plan between single start to multiple goals or multiple start to single goal by pre-processing and computing a motion library. There is also a very recent method on theoretically finding any start to any goal, but because of the choice of representations, it does a many start to many goal constant time planner. So how can we are interested in finding pre-processing, doing a pre-processing such that at runtime you can find a solution from any start state to any goal state within a constant time, within a user specified constant time. So for that, we are going to be using the GCS representation and what it looks like. And this is an example of how a motion library can look like for the GCS representation. So you want to pre-compute these motions that take you from the boundary of every state to the boundary of every other state. And that basically means that you have n choose 2 number of region pairs to pre-process, right? Where n is the number of non-adjacent regions. But then the promise of GCS is that this n can be low. Like potentially, empirically, I've seen that if there are large parts of the state space that are mostly static, we can just decompose that configuration space into a single big convex set. And we also have IXG star, which can now find bounded suboptimal solution with its effort proportional to the difficulty of the query, and it's also parallelizable. So this can lead to constant time insight, which can give you any start to any goal, constant time planning. And if you're able to do that, then basically replanning falls out as a byproduct, right? So just as a working example, how can we go from, like we wanted to not compute all possible candidates in our library to go between any regions. like, for example, in this case, if you want to find out how to go from 1 to 5, there are so many possibilities, like 1, 2, 4, 5, 1, 3, 4, 5. But if you want to limit the number of possibilities, then we should be able to find the maximum cost of the potential solution between those two regions. And in order to find that, we compute an upper bound of what the cost can be within a convex set. And how do we do that? So if you assume we are having these polyhedral representations for the convex sets, and then you can formulate a max min problem to find, this is basically similar to finding the largest diagonal within a convex set, but because your trajectory representation can be more sophisticated than just a straight line, you need to do something a bit more complex than to find this upper bound. And once you have this upper bound, this is an example of how you can, like the upper bound, how it looks for different decompositions in your space for different convex sets. And you can use this upper bound to compute this motion library, right? So what you're seeing here is a 2D example of this environment being decomposed. The red polygons here are obstacles. So the environment is decomposed into a bunch of convex sets. And you have now computed a motion library that can take you between any 2 points that are on these green convex sets. So at query time, when you get a query to go from any point in the green convex set to any point in the other green convex set, it is sufficient to just evaluate over these candidate paths to get a constant time solution that is globally optimal and smooth. So how does that constant time query happen? So you have a hash lookup of the candidate paths. Then you have to do query satisfaction because the start and goal state can be at different points within those green regions. Then you have to do a refinement and you have to take the minimum. So 3 of these 4 operations can be constant time if you know the size of your candidate library. The optimal refinement is not constant time, but I was just reading that there are some recent work on how can you bound this. If the optimal refinement is convex optimization, then you can bound that to a constant time depending on how far is your optimum from your initial state, search state. But for now, you don't have to do this, right? You don't have to do the optimal refinement. You can just do these 3 things and get a solution, and you will have a constant time solution. So that brings me to the end of my talk, and I wanted to once again list the contributions and the different places where these works have been published. I wanted to take a minute to acknowledge, so my advisors first, Max and Howie. This has been one of my, definitely PhD was the best part of my life by far. And I thank both of you for giving me this incredible attitude to basically go ahead and do whatever I want, and also supporting it. Also thank my committee, Zach and Russ, and also thanks to Russ for having me in his lab to present. Then I wanted to thank my collaborators first, with whom I developed all these ideas. Then Itamar and Yorai, who we have collaborated outside research. All the people in SBPL and Biorobotics Lab, and also the RI community. I think the RI community definitely has a very different, this is the place to be if you wanted to do robotics. I think we think system first, and we wanted to make robotics work, and then we work backwards from there. I think that's a very important mentality. My family, both my parents and my brother from the other side of the planet, they have been very supportive during these years. My wife, who has been very, very wonderful and supportive like the last few years, and my dog Hanu, for being the best companion. Cool. With that, I'll yeah.
Thank you, Ram, for compressing I guess the 6 best years of your life in an hour. With that, so the process is that we're gonna have questions first from the committee, and then after those questions get answered, then we're gonna go to questions from the audience. Okay, and as far as the committee goes, usually it's the person who is an external member of the committee that person goes first. In this particular case is Ross. Ross, unless you have objection, maybe you can go first.
I'm happy to go first. Would you like me to ask all of my questions now, a subset that is public and there's a private after, or would you like me to do a few and come back? What's your preference?
Yeah, so typically there is no private here, meaning that, all the questions get asked publicly, but then afterwards, it's just a discussion within a committee members without round. So it's like basically just the committee members will have a discussion afterwards about the decision and the feedback. But there is no like a private questioning part. So all the questions are public. Whether you ask them all in one single shot or you do it kind of in a round robin fashion, it's entirely up to you. More often than not, then they get asked all in one single shot, but it's definitely entirely up to you.
Okay, let's see how it goes. Maybe, I mean, my high level feedback is it's a ton of great work. I just really like the portfolio. And of course, the thing I've always been pushing you on is that I like you to be a little bit more crisp in your statement of exactly the statement of the contribution. So maybe just on the GCS side specifically, I love the work. My view is that what you're saying is that there's a family of problems that GCS can represent. And some of them admit simple lower bounds and upper bounds like you found, and then INSAT GCS can solve them very quickly. But maybe you have to be more careful about saying, like, if you want to say you solve every GCS instance, then you haven't met that burden of, the burden of evidence would be to solve the hard GCS instances where the constraints are dominant and it's not easy to find upper bounds and lower bounds, right? So maybe could you clarify a little bit where you say you have stronger theoretical properties? I know you mean by the repeated visits, and then, like, when do you actually have these performance benefits?
Yeah. So, I mean, it's not strictly superior in terms of the planning efficiency, right? We only find it empirically that in many cases that we are able to solve it faster. And I also only focused on the motion planning problem, like you said. So it's a more general framework, and you can encode like harder problems. And I haven't at least evaluated for those hard GCS problems. But in terms of the lower bounds and upper bounds, you can, I mean, as long in my opinion, at least, like both the lower bound and upper bound calculations are pretty general purpose, right? So they are not very tied to, you're trying to find the upper bounds within a convex constraint for every one of them in your graph, and you're also finding these lower bounds between those non-adjacent convex regions. So that calculation is, I think, general purpose, but in terms of the planning,
the hard one is the upper bound, right? So you're doing the relaxed GCS and just taking the straight lines. But if you have a highly constrained problem, then finding any feasible solution requires putting, the entire graph into memory and all of the costs and constraints into memory. And I think that's the hard case, right? Finding in a complex constrained optimization, finding any upper bound is tough, right?
That's so that's why, so you don't have to do that, right? Like I mean, I think the alternative is that you wanted to find these upper bounds within every single convex set. You just have to load one convex constraint into memory, and then you have to find how worse for your problem specification you will perform within that convex set. And when you have the whole planning problem now, you can run a search in just the abstract graph space without loading all the convex sets. And then you can add up these upper bounds within these convex sets to find the overall upper bound along the path. So that is better than starting with infinity, right? As an upper bound.
I know you and Xiao have talked a bunch. I think there are cases that is very hard to do. Even the max min in a highly constrained case, I think is not as simple as you say. But I think I don't mean to grill you on that, but I think you have to be a little careful, I guess, about saying exactly what works and what doesn't work, right? I mean, I think that to say that you solve the entire GCS set of problems better would be there'd be a big burden, I guess, to solve that, right? To say that.
Yes, I'm not claiming that. Let me be clear. So I'm not claiming that, once again, it's not strictly superior. For the class of problems that we looked at, we just found it to to be empirically better. And you're right, this max min problem is not, it's not easy for in the general for the general case. But once again, like if you can find some relaxation to, like for example, I'll just be very specific, right? So you the planning with contact paper that Bernhard had, where you have this QCQP problem and you propose a SDP relaxation. That SDP relaxation can be the min problem of the max min problem, right? Now you can solve it for different like the outer max and max. Of course, because you're using a relaxation for the inner min, it's not going to be a provable upper bound. But I think it'll get you there. So
No,
there are
but that problem is bad if it's not a polyhedron. Like I don't think we have good ways to do that for a spectrohedron, right? So I think polyhedron case specifically, we have some algorithms that will bound that max distance, but in general, that's a non-convex problem, right?
Yes.
I think the spectrohedron is a harder object to do that reasoning over.
Mm-hmm. Yeah, I agree.
Maybe you know something I don't know, but I don't know how to do that for a spectrohedron. I haven't thought enough about it, but I don't, off the top of my head, I don't know how to do that.
Right. So, yeah, I don't know either.
Polyhedron case is a very special case for that.
Agreed. Yeah.
Okay, maybe just a couple other to go in different directions, and maybe Zach will lean more into the contact implicit, but I'll just at least ask. So, it was interesting to see that the choice you made for breaking down sort of into the discrete pieces was not maybe what I would have expected out of the box, right? So you actually break it up based on joint angles, I guess, if I understand correctly, right? And so you're sort of saying that within some, narrow slice of joint angles, I hope contact implicit trajectory is going to be, and I know you don't say that is optimal, but again, you're relying on the contact implicit form of the trajectory optimization to work if you bound the joint angles to be in some small domain.
Yes.
But there's other ways. There's a natural discretization of contact, no contact, or other things like this. So how did you end up picking that, and how strong do you think the contact implicit results given you've bounded? Like, why is that the natural decomposition of the space?
Because I think if you're just purely searching in the configuration space, and if you have a perfect model of the environment, then you can find the contact mode knowing the configuration of the robot and the configuration of the environment, right? So I didn't have a need to explicitly search over the contact modes, but rather because I can always calculate the contact mode using the configuration of the robot and the environment. So that's why I chose that representation. And because, like you said, like we are only solving this contact implicit optimization for very small problems and then putting them together. That's why I think that's why it ended up working, and that's why I also chose that representation. But I know that in the contact literature, like even Shani's work, or it's very common to search in the space of contact modes and enumerate that. Yeah, and I think even once again, even Bernhard's work was you build those convex sets for each of those contact modes, right? Yeah, but this was my reasoning, that you can always calculate the contact mode if you know the configuration of the robot and the environment in model-based planning, at least.
But if you say that, then why did you use contact implicit instead of contact explicit?
So contact implicit, I think what I was trying to say there was I was just using that penalty-based method, right? So once again, I don't know the exact contact mode. I don't have to even calculate the exact contact mode the way people in the contact literature do it, right? So I just have two configurations that are in contact, but I don't have to know whether if it is the same contact mode even. Like it could be in the same contact mode, it could be in different contact mode, but you're just trying to see if there is a trajectory that can connect them. You don't have to even know that explicitly. So that was the idea there.
I agree with that statement, but that seems inconsistent with what you just said about saying you chose joint angles because then the contact mode sequence is clear.
Yes, I mentioned that statement to justify that you don't have to. They both are they both are analogous. Like you don't have to do it the way where you have to where you explicitly know enumerate over the contact modes. I was just trying to explain that parallel. Yeah.
So why is the joint angles the right way to decompose the space? Like, yeah, I mean, I thought your answer to that just now was that it basically almost prescribes the context sequence. But then we just, it doesn't prescribe the context sequence. So why is the joint angle, why are the joint angles the right way to sort of do your discrete decomposition? And in practice, like how often, I mean, do you suffer the contact implicits? I mean, those can be nasty optimizations. Zach's worked a lot on them. I've worked a lot on them, but they're not great. I mean, maybe Zach's are better than mine. And those are still hard problems. Do you suffer even in once you've narrowed? I mean, how narrow maybe do you have to make the contact or the joint angles in order to make those optimizations successful?
So for the experiments that I showed, we had a different resolution lattice for different joints. I think it was two degrees or something in terms of degrees for the distal joints, and 1 degree for the proximal joints. So that was the discretization. But I didn't have so the search methods are with this discretization, the search methods are pretty good in terms of exploration. I mean, I'll also tell this: the experiments that I showed, though, that they take 10 to 15 minutes to solve. So it's not if we are not running, it's an open loop execution. We are not running it online. So it takes around 10 to 15 minutes to solve. I didn't have the parallelization approaches at that time. Those were developed later. But there were a lot of bells and whistles in terms of lazy evaluation and in terms of like reducing the rejection that you were of the solution that you're getting from optimization. But the answer to your question is, so that was a discretization. The reason for choosing joint configurations is that in my head, it's enough to search in the space of joint angles, and you don't have to explicitly think about contact modes. And within the joint angles, you can just use contact implicit optimization. It doesn't have to be the case that those boundaries, like the boundary conditions, are within the same contact mode or otherwise. So that's not needed, and that's the reasoning.
Okay, I'll ask one more and then I'll pass the torch, I guess. So maybe even backing up even to the closer to the beginning. So for the quad rotors, it's kind of a similar question, but maybe in the easier case since there's no contact involved. But so you made the choice to use differential flatness, but then you solved it with a variable time horizon. Like the differential flatness is a convex optimization if the time horizon is fixed, except for input constraints and stuff like that. But then you solved the kind of maybe surprisingly harder version of it by doing the time varying, the unbounded time, and then it became non-convex again and everything. So why choose that? Like why, if you're gonna allow time to be flexible, for instance, what advantage do you have from using differential flatness? Why not just solve the original trajectory optimization problem, or why not fix the time and then enjoy some of the benefits of the flatness representation?
So I didn't. First of all, like the optimization there I didn't mention it in the slides, but it's a joint polynomial optimization. I'm just representing something like B-splines. That's what I'm using to represent the trajectories for the quad rotors. The time for the time variable, it was if I remember correctly, the time variable was a penalty. So without the time variable, you're right. It's a QP. With the time variable, it was not a QP. So to answer your question, like why use? I mean, I think the flatness. I was just using the flatness to impose constraints on the direction of the acceleration when I was fine because in the full dimensional, I think there was actually a typo in that slide. So in the full dimensional space, you have the sorry, let me go back to in the full dimensional space. So you have XYZ roll and pitch in the low dimensional space. In the full dimensional space, when I say the bold X, I just had XYZ, no roll and pitch angles, because you can always calculate that once you know those derivatives, right? So I was just optimizing for polynomials in the XYZ space with constraints on the acceleration that are coming from the from the roll and pitch angles in the low dimensional, from the low dimensional search. So there is a penalty version of the optimization, but the optimization is only happening in the XYZ and its derivative space. There is no angle there.
I mean,
and-
maybe lift it up. I mean, I think I understand what you implemented, but so just to lift it up, like, what is your recommendation if we want to use inset star everything? Then where do you just, is there a principle to decide how much you lean into the continuous optimization? Like, do you prefer convex formulations now? Do you throw in, trust nonlinear optimizations? And are there maybe principles for deciding the discreteness? Like, is there, I'm just trying to find the pattern kind of here of like where you're trying to break between the discrete and continuous. And I wonder if there's like a, advice that you'd give given all your experiments.
Yeah, so I think if mostly in almost all my experiments, I've used the configuration space of the robot, whether it is a manipulator or a drone, as the discrete, as the low dimensional graph. The reason is obstacles. I think purely it just boils down to dealing with obstacles, and search can systematically explore spaces around the obstacle. Yes, I mean it is strictly better off if your optimization can be convex in that ancestral path. It does not have to be. We have the inside stars optimality criteria is under some assumptions on the behavior of the optimization. But if I were to, I mean, there is no, I think the best principled answer that I can give is use the variables for which it's hard to encode constraints in the optimization as your low dimensional search. I haven't done a ton of exploration into picking arbitrary low dimensional variables. I wish I did that, but I didn't do it. I always had this expert handpicking of what should be the low dimensional variables, but that's the answer.
Cool. I fear I've taken too much time, so I'll pass the torch wherever it needs to go.
All right, thank you, Ross, for great questions. Zach, do you want to go next?
Sure. Yeah, I want to second awesome work. I love this stuff.
Thank you.
I think it's super cool. Let me poke maybe then at some of the more continuous optimization stuff. And I think some of the stuff that you just said, yeah, I think in response to Russ's questions got me really thinking about, so you said like, I think I want to dig in on where the dividing line is a little bit more. I think it's very natural to do what you did and double down on, like the regime in which the search stuff has historically been used in just obstacles and configuration space. But you said, you want to use that stuff for when it's hard to encode constraints. I'd argue, convex obstacles and things like this are really easy to encode. And something like the nonlinear dynamics of, like a legged robot or something are super hard, especially if you're doing contact implicit. I'd argue like the contact implicit dynamics of some, articulated robot, way harder to encode than like stay out of this convex, couple of convex regions or something like that. Thoughts on that?
This is interesting. I mean, unfortunately, I don't have any experiments to back that up. Like I think you can.
So maybe I'll pose it slightly differently.
Yeah.
If you were trying to represent the feasible set,
Yeah.
in both cases, I can draw you on the whiteboard the feasible set of some keep out of these obstacles. And maybe it's, it's some non-convex inequalities, but I can write those down and I can draw it, right? If I asked you to draw me the feasible set that satisfies the constraints for some 7-DOF manipulator arm,
Yeah.
could you draw that?
No, you cannot. Yeah.
Okay. How do you write it? You can't even really write it down, right? It's some weird set of differential things that you have to always approximate through some ODE solver or something, right?
So
can you tell me what that looks like just in the, say, high dimensional state space of the robot? What is that geometric object?
I don't know, but I think you're I mean, so the question that you're asking is like, what if I use if I discretize the nonlinear dynamics and search in that space for the
not necessarily. I'm just I'm trying to poke at the initial statement that that's somehow easier to encode. I would argue it's not at all, right? it's some weird, crazy high dimensional manifold that can be arbitrarily weird, curvy, and
But that's what you're not dealing with that in the optimization, right?
you
So,
are dealing with that. That's where all your dynamics are going into the continuous optimization, right?
yes, but we are not, I mean, we are not explicitly dealing with obstacles in the optimization, right?
That's right, yeah.
So-
I agree with that statement. That's great.
So, it doesn't matter how the free space looks like in the high dimensional space, right?
Oh, no. You're saying you're putting these differential dynamics, these ODEs representing nonlinear dynamics. That's some constraint manifold, right?
Yes, yeah.
It's like arbitrarily
Yes.
curvy and weird and nasty, right? That I would have a really hard time encoding the feasible set there. In a sane way. I guess I'm just pushing back on like what's easy and what's hard.
Yeah,
here.
yeah.
And I guess one contention is like, let's go with like, if you wanted to bring more of that into the search part, what would that look like?
So there are there are some simple experiments on like cart pole or pendulum for doing value iteration, like discretizing the whole dynamics and doing value iteration, right? So if you use those discretize the dynamics and you search in them and satisfy obstacle constraints in the full dimensional space. Let me think. So I mean, I think it's definitely possible. You're right. I think if you think about it, like it's obstacles are definitely more intuitive than the nonlinear dynamics. So you might benefit more by searching in the by discretizing and searching in the across nonlinear dynamics using search and imposing these obstacle constraints in the full dimensional space.
It's okay. I'll move on. But yeah, I just wanted to poke at that assumption because I think it's
not an
where you draw
assumption.
the line is
Yeah.
really, I think, like deeply interesting, and I think maybe something that's
Yeah.
still kind of left for us to.
Yeah, I think I was asked this question several years ago at a conference, and I just didn't pursue that line. I should have.
I mean, it's super interesting and like really deep question. Cool. Anyway, one just a few little ones. So I think around slide 36, I wanted to ask something about like in these subproblems, are you ever pulling some version of the obstacle constraints into the subproblems?
No. So
I think, yeah, here you said something about this. Yeah, like you can solve the continuous trial problem and end up sort of violating constraints, and then you're like pruning these, but why not?
Why not? So if it is, for example, in the GCS case, you're naturally handling it, right? Because you're at least the motion. Yeah. But otherwise, like why am I not doing it? I think it's just a choice. There was no strong reason why I was not doing it, because I was able to look at whenever I have the optimization running, I was able to have, in terms of implementation, have callbacks to see if the obstacles or constraints are not violated and the other constraints are satisfied, just use that solution and move on.
Okay. Yeah, I think it wouldn't be too bad to start throwing in, convexifications or linearizations of.
Yeah, I mean, I know Kevin Tracy has been doing a ton of work. I really wanted to use some of his work. I did think about this at some point. I just didn't.
I'm just curious.
Yeah.
I was wondering also on the drone stuff. I think I wrote this down around slide 50. Like, what does your objective function look like?
It's for that it's minimum jerk plus it's a combination of weighted combination of minimum jerk and duration of the trajectory.
Okay, so you're actually, you're solving some sort of like minimum time formulation.
Yes.
Times explicitly is it? Yeah. So I was wondering, like, what about including time in the graph search?
That's totally doable. I mean, it's we do it all the time for other applications. Just that we didn't do it for this one. That's a very good. I don't know why I didn't do it for this application.
So the reason I asked you, I think Russ was getting at this too. Like, I think why I would use these graph search techniques and interleave them is to make the trad job problem easier.
Yeah.
And convex, and like, if you include the non-convexity in the graph search, like T is the thing that makes
That's true.
the trad job problem non-convex, just like the obstacles, right? This is about, similar to my question about the dynamics, right? Like, you want to be moving the non-convex annoying stuff into the graph search because it's good at that.
Yeah.
And then like let the trad job stuff solve nicer problems.
Yeah,
And just like the obstacles, right? Including T in the graph search makes the trad job convex now.
yeah, yeah.
So like, you know what I mean? Like,
That's true, that's
so
true.
this is kind of the choices of where you draw the line, I think, are really critical, and like, I guess it's a design choice here, but thinking deeply about, you know,
Yeah.
where to stick what, I think is.
This was definitely a low hanging fruit. I don't know why I didn't, do this.
What else? Okay,
Yeah.
then the last thing I wanted to poke out a little bit, because we've been doing this a lot lately, and I'm curious about your experiences with the Mujoko setup, and I wanted to ask some specific questions there. I guess this is like 60-ish, if you want to pull the slides up, but I was curious, this custom virtual contact normal and friction force models, what does that look like?
Yeah, I have, I had the math there.
I do get
was-
to tell me out loud, you don't have to go super crazy.
I mean, it's basically the custom, friction normal force models are just giving you force from a distance. So in addition to Mujoko's soft model, you're having a force from a distance that I'm adding to the normal contact normal forces.
So you were adding this into the dynamics constraints,
Um,
not in the objective.
so the model parameters of the contact model are in the objective.
You're taking Mujoko's, or so your,
No, the model parameters of my virtual contact model are in the objective.
so you're optimizing over your like,
Yeah, because that is helping me. So there is the Mujoko model is soft, but then like it's not as soft as the optimization would like it to be. So that's why I'm having that contact model, and then there's this virtual both friction normal model and contact normal model and friction model that is just trying to break the discontinuity. And basically the optimization is some kind of log barrier style approach, right? So you're starting with the set of parameters, value for these parameters that help you converge earlier on, but then you're also optimizing for the value of the parameter simultaneously.
so you're like penalizing them to drop.
Yes, yeah.
Yeah, okay. Yeah, I think I would probably second Russ on this, and that like, you know, again, like trying to make the sub problems nicer. Contact implicit is super gross and super hard, and like, why not make that sub problem nicer by throwing more of that into the graph search, I guess, you know, by doing something more, like if I were doing this with this kind of, you know, discrete representation mix, I would 100% like try to do something to get at the contact modes.
Yeah.
There without like, because like these, maybe it's also another way of saying this, these trad up like contact implicity things, they're fundamentally bi-level optimization problems or multi-level optimization problems, and they're just horrible from a complexity perspective and everything else. And like everything you do there is a hacky heuristic to try to, you know. So you implemented like custom hacky heuristics, you know, to like smooth that problem out instead of you know, rigorously dealing with it in these graph search methods, right?
That's true. Like I think coming from so I think my goal was that I want to have a toolbox in Mujoko that works for all the contact problems. So I was just focusing on how can I use the contact models Mujoko has and write an optimization that this was originally promised by Emo.
Yeah.
To never happen, but
I know. Well, it's sort of happening, but it's
Yeah.
it's still messy. We're working on this right now, actually, with those guys, and we found that just as a like fun FYI thing, and I was curious what you were doing here, because we're trying to do co-location on top of the Mujoko stuff, and it absolutely does not work. And their gradients, specifically if you're in penetration, are just completely useless.
Useless, yeah. But then like that's what I've been using to get this contact configuration though. It is useless.
Yeah.
But then the normal direction is useful to build the graph. It is
So-
like absolutely, the values are absolutely useless, but the directions are pretty useful.
Yeah, maybe for the graph stuff, yeah, we have not found that you can trust any of it as soon as you're in penetration, it completely fails, so you have to do, so like, this is why I was wondering about your custom virtual contact normal stuff, I feel like you basically have to do something like that, because the stuff coming out of the contact model is just not good enough.
Right, yeah, but this was mostly helping when I was not making the penetration, right, because like the penetration is being handled.
Yeah.
Yeah, but then of course, like the when you're trying to lift these edges to full dimensional space, there might be penetration again within the optimization. Yeah, but otherwise, you're building the graph.
Yeah, I don't want to take up too much time, so I'll pass the torch.
All right, great. Thank you, that. It's been a great discussion so far. How are you?
Yes. Okay, so let me first join in with the others who have complimented you on your presentation. And for Max and me in particular, we got to see you, how you were so many years ago and how you are now. And it's just, first, this presentation was excellent, and the improvement also just incredible, it's inspiring. You did a great job packing in a lot of information in, like you said, the best 6 years of your life into 55 minutes. So that was great. I also want to thank you for your hard work and the insight that you brought to us, especially spoon feeding me all the stupid questions I'm afraid to ask in front of Max, but he's not. So with that, I just want to give you that compliment again. But I'm going to ask you just 2 quick questions because I'm a little bit worried about time. And if it turns out either of these questions is a long discussion afterwards, then we can save that for afterwards, because again, these 6 years aren't over yet. So the first question is, it sort of builds off of, I think of what, maybe in some ways what Russ and Zach were saying a little bit, about this assumption that your free space can be broken down to these nice, either polyhedron or something that can be readily discretized into a graph. And I worry, what about that robot arm, that 70-degree of freedom robot arm, or what the hell, snake robots? I just, because these pictures you show, everything's nice and polygonal. Yeah, what is the process that you think in implementing this for those kinds of robots that we can follow? So this will be trackable.
For the decomposition?
For anything, either the decomposition or just in the original instat work.
Yeah, so I'll answer the decomposition. I think the decomposition, once again, Russ's group has been working on building these. In general, the decomposition is hard, I agree. But Russ's group has been working on doing this, extending the decomposition methods to configuration spaces. It is a nonlinear optimization, but they have been trying to make progress on both sides.
You already told me that once before, and I think it's a good answer to say, we'll just let Russ figure it out.
No,
But putting Russ aside for a second, which we shouldn't do, but this is for fun. What would you do if we didn't have Russ?
So you can first of all, you can always use insat without relying on decompositions, right? It's just going to be slower with all these assumptions that might not hold true.
How do you create the graph then? We just try configurations at random and connect them like a PRM, or what would be your?
I think for a snake, for something as high dimensional as snake, I either will go with some like hand designed lattice, or go for like sampling based exploration.
So let me push you on that lattice thing. Okay, so this is still part of the first question. The second task you had, was like contact planning, whatever, but it was meant to be in confined spaces.
Mhm.
So I worry, how do we either generate that graph in a confined space? Because I don't think we can hand throw it, or if you're using the decomposition, common answer people say is, well, we'll have lots of little cells that would fit into the nooks and crannies of the free configuration space, but then you get this complexity problem. You said before n would be small for the GCS, but now. So what's the approach? What's the paradigm here to deal with the really confined spaces within narrow corridors in C space?
Yeah, so uniform discretization, if you know like how narrow your narrow corridor is going to be, uniform discretization, you can.
But we don't, it's hard to know what that narrowness is. For a robot arm or a snake robot in the configuration space, it's hard to know what that narrow corridor is.
Yeah, so you can do something like, I think adaptive discretization, like you start with some coarse discretization, but then like, if just once again, like, first I'll answer how can we handle it when you're discretizing, and then like maybe go into sampling. So if you're just discretizing, then you can start with some coarse discretization, and then if your search is not making progress, and you can tell from your heuristic that it is getting stuck in a local minima, then you can adaptively like increase the resolution, and that's one way to make
One thing I commented on in the text, and I saw it here as well, is when you say, it's as if you're building the graph as you're going along also, is that correct?
yes, yeah.
So you have them, okay, so I'm gonna pause there, and you, just to be clear, you're building, I'll say this for afterwards, because I'm too tired to formulate my question, actually. So my second question is, it's a more philosophical question, and we've all talked about this before, maybe Max and I have talked about this before. Just as Zach and Russ pointed out, there's this trade-off of, you know, what should be discrete, when to continuous. That's a nice question. Another thing about your work that I like is that you have this deferred computation thing going on. In other words, you're not computing everything, which is cool. Do you have any insight as to what the right way to defer computation should be? Is there a guideline, or is it just use instat and?
No, there is some, so I think, you can, there is a principal answer, and then there is a, you can try to do it, try to figure it out when you make an implementation. I think the, principal answer is, it falls into the, problem of doing lazy search, right? Like how much can you defer from, and in this context, basically lazy means that how much can you defer from doing the full dimensional optimization or the expensive part of your, whole search. So but at the same time, you don't, the full dimensional optimization is informing you and helping you search in the correct directions. So you don't want to defer it too much also. I think the trade-off there can be met by having a quick way to estimate how, like what is the cost of the operations that you're deferring. If there is a quick way to estimate that, then you can use that to still do a good job. And in search, this boils down to having a estimating a lower bound without to not sacrifice any properties. And I think that's the
I'll stop there because I wanna hear what Max has to say.
yeah.
Well, yeah, I'll ask only a few questions because we have a hard stop at 12 o'clock. I want to make sure that the audience also has time to ask questions. One is the whole thing about the expansions. If you think about it, many problems, you probably don't have to revisit the same state over and over and over again.
Yes.
Right? It's probably revisit it once.
Yes.
More.
Yes.
That's it. So why not do like a graph search where you don't allow re-expansions, but you augment the search space with a number of revisits and fix and limit to two.
We did that, right? Like actually for the quadrotor application, we had an augmented graph.
Okay.
Yeah. So and then we limited the number of cycles. And when I say re-expansions here, so once again, like the re-expansion can be just turning off duplicate detection, allowing for it does not have to. So re-expansion can mean that you're allowing for cycles, but in many examples, I was not allowing for cycles. It's re-expansion, meaning you can have that duplicate node in the frontier, but it is without cycles. So every time I make an expansion, I see if the successor that I'm generating is not in that ancestor. Only then I allow for re-expansion.
Okay, so then we effectively become, it's not a combinatorial problem in terms of the number of paths. It becomes only twice the size of the graph.
Yes. Yeah. Yeah.
The other question is, when you do the graph search, right, and you effectively kind of relying on this expensive edge evaluation. It's not an edge evaluation, you're trying to recompute the g-value. It changes how your local minima effectively looks in a way, right? Like, in normal graph search, we have a lot of different, all kind of different heuristics that try to make sure that the local minima are not deep enough. Here, it's entirely different, right? Because you're effectively relying on some other process, like a predicted optimization, to reevaluate and potentially figure out that this node is no longer valid. You can't just get to it. So Any thoughts on what implication it has in terms of how to deal with the local minima, but any ways to compute heuristics better,
Yeah,
knowing that, that's the structure of the problem.
yeah, so, because, one thing, like, because my works, were mostly focused on, planning for dynamical systems, the heuristics, I did some work on, actually, I didn't talk about this on this slide, but INSAT star, has heuristics that are being computed, assuming separable cost structure for control affine systems. So it boils down to making assumptions about the system. Control affine is a very reasonable assumption, and we developed lower bounds for control affine systems, and those values were, I think I can go into, I had it maybe as a backup slide or something. Yeah, so I think so for control affine systems and separable cost structure, we can compute these, we can compute a necessary condition for, I mean, this is obviously not considering obstacles. So that's why this, I can explain the terms here, but you can, yes, we have some custom heuristics. These are lower bounds on the solution cost, at least in terms of the action cost. So we can use these things for computing heuristics. But is that the question? Is the question about like how can you compute heuristics for systems like these, or is it more because you're asking about cost to come more than?
Well, I mean, the cost to come is something that you're evaluating, but eventually, the cases where the cost to come exceeds whatever the bounds you have on suboptimality you can tolerate, or if it becomes more infeasible, right? Then that creates its own local minimum. And I don't know if those heuristics here are sufficient or not to overcome.
So if you're saying cost to come exceeds something that you can tolerate.
In terms of suboptimality, if you're going for suboptimal solution, right? And if you're going for particular suboptimality and then the recomputation of the G-value becomes way over it, right?
Yeah.
Then you're effectively saying, okay, that's not good, right? And that creates its own.
Okay.
So and then maybe, like that heuristics that here, based on your experience, do tremendously help with those type of local minimum. I don't know.
Yeah. I still don't get so the question is like, how can you escape such local minima that are coming because of
Yeah, what's your intuition basically? How much more complex it becomes to design a heuristic function in the context of INSAT stuff? Or INSAT.
So you can, I mean, to create admissible, provably admissible heuristic, it's not easy. This is provably admissible. Now this one does not have any obstacles into this formulation, right? So the obstacles can still create local minima. Now, if you add those, if you use some heuristic for obstacles and then add them with this, and I don't know if this is admissible again. So there is a general purpose solution, but it is whether it is informative or not, that depends on the problem at hand. Yeah, but you can always you always have search techniques like multi-heuristic, where you can use different heuristics even if they're inadmissible, and still use one anchor heuristic that is admissible, right? So.
Okay, all right. One last question before we go, more general, like, so INSAT is perhaps one way to interleave search and trajectory optimization in a kind of one single algorithm framework. Do you see that potential venues kind of for other algorithmic frameworks that interleave in an entirely different way?
GCS actually does that, right? So they solve they're not interleaving in the sense they're solving the whole problem in a unified way. So that's that's,
So given more general, do you recommend that people kind of continue and look at other ways to interleave, or do you think it's basically those two, that's it, that's enough?
I'm biased. I think this is the correct way to do it. But other ways to interleave, when you suggest search and optimization, or it could be anything.
Search and optimization specifically.
Uh, um, uh, you can, I mean, you don't have to interleave, at this frequency, you can interleave, with a different frequency. So
Right.
but that's not the answer you're expecting, right?
Yeah, okay, so one could think of doing optimization as the main thing and then invoking search somehow at a particular point of time. That's, as
Yeah.
opposed to doing it that way. So but I don't know. I mean, I was just looking for some sort of intuition more generally whether there's worth exploring in the future or not. And, that might be to think about it and then, put it in your conclusions.
Yeah.
Doesn't need to be answered now. Okay, all right. Any quick questions?
Yeah, sorry. The gallery here, since we only have like maybe 15 minutes.
Questions from the audience?
We can deliberate quickly, then I'm fine.
What? So let's say there's a interesting question.
I guess to connect what you were just asking about, there's something called generalized vendors decomposition for like fixed integer convex programs. The exact form of it is going to depend on what your convex program looks like. But the GCS 1.1 version, what generalized vendors decomposition does is it turns this into a like mixed integer linear program. It basically generates a candidate sequence of sets. And then you solve the trajectory optimization problem through that sequence of sets. And it gives you a linear constraint you then add to your mixed integer linear program to resolve. So
Okay.
that would be a different way to solve this where basically you do your thing as something that generates a sequence of sets and then something that evaluates that sequence of sets and gives you a lower bound on cost.
Yeah.
The insat's just a different way of generating that sequence of sets via search instead of via mixed integer linear program. I don't know if there was a question there or not, but
Definitely worthwhile to have it perhaps in a related book. Okay, any other questions? No, no? Okay, last question for Rich.
if we had another 6 years, that would be good.
VLM.
Fantastic. All right, okay, all right, well, thank you very much.
Thank you.